Welcome to this lecture in which we address mechanical separations. It's good to have an idea of typical scales in separation processes. There are microbes and cell debris at a factor 10 smaller. There are multiple technologies that effectively filter out particles that are larger than 1 to 10 micrometer. These are called mechanical separations. Then there is a good set of molecular separation techniques, such as extraction and chromatography, that isolate small dissolved compounds of several nanometer size. In between, in the colloidal range, there is a gap for which there are still few suitable separation techniques available. In industrial biotechnology, mechanical separations are always used to remove cells and sometimes for removing other particles such as crystals. We will treat mechanical separations now and in the next lecture, molecular separations. Firstly, we should know where our product is. Fermentation broth contains cells and extracellular liquid. The cells, indicated by the spheres, contain oven-dry matter, indicated by the white axis, and intercellular water with a bit of other volatiles. Products will remain intercellular if they do not pass the cell wall. For example, the storage polymer polyhydroxybutyrate or an intercellular protein. To obtain intercellular product, the cells will have to be disrupted, which releases a multitude of side products. Products will be largely extracellular if the cells will actively excrete them, for example lactate or excreted enzyme. Then one will recover extracellular liquid and wash the cells, the wet cells, because some liquid, including product, adheres to the cells. Products that consist of small and uncharged molecules, such as ethanol, but also PDO, may spontaneously and quickly partition between intracellular and extracellular liquid. After separating extracellular liquid from the cells, thorough washing of the cells will also remove the intracellular portion of the product from the cells without cell disruption. So, for each of these product types, we need a method for separating cells from liquid. Then, depending on the product, we need cell disruption or cell washing. So, in many mechanical separations, it will be important to know how much liquid still adheres to separated cells and which part of the cells is dry matter. Typically, cells contain about 25% dry matter. The fermentation broth will also include extracellular liquid. In fermentations that were pushed to extreme limits, about 70% dry matter was reached, considering the whole fermenter. But the treated PDO fermentation that reached 8.5% dry matter is already impressive. At about 17% dry matter, broth is a cream that can still flow out of a centrifuge or a microfiltration device. This may tell us how much extracellular liquid remains after centrifugation or microfiltration. Recovered wet cells on mass basis will consist of about 70% dry matter, 50% intracellular water, and 33% attached extracellular liquid. Later, this can tell us how much washing of cells may be needed. One useful operation to remove cells from broth is centrifugation. Like in sedimentation, particles get a velocity proportional to the density difference of the particles with the medium, which is small for cells, the particle diameter, which is also small for cellular particles, or the acceleration of the force field, which is the gravitational acceleration g for sedimentation, and is the centrifugal acceleration omega square r for centrifugation. Sedimentation is too slow for cells, but by rotating quickly at high omega and by using a large rotor at high r, centrifugation rates can be up to 10,000 times faster than sedimentation rates. Continuous operation is possible, like for almost all DSP operations. Filtration is familiar to everybody. However, dead-end filters, like we use in the kitchen, are not so useful for cell removal. cells will form a layer on the filter that blocks liquid flow. Instead, cross-flow filtration is used, in which the cells are kept in suspension. Cross-flow is achieved by a high rate of cycling of the suspension along the retentate side of the filter. The filter is a membrane with pores smaller than a micrometer to retain cells, leading to the term microfiltration. Removed cells usually need washing, with diafiltration as one of the options. Then, extracellular product distributes evenly between the wash water and extracellular liquid. Countercurrent operation is useful. We can use the separation factor in the Gramsci equation. The separation factor includes the flow rate, but also the partition coefficient between the two aqueous phases. That coefficient is not unity because part of the feed does not participate in the equilibration of the solutes. For example, assume that Fv kg per hour of wash water is contacted with Fl kg per hour of recovered wet cells that include 33% attached liquid. The partition coefficient between V and L phases is K is 3 for an extracellular product, because only extracellular water participates. If the product can freely pass the cell membrane, intracellular liquid also participates. That translates into K is 1.2 during washing. Such a K value calculation will be used later in the PDO case. For intracellular products, cell disruption is required. The methods used in industry are quite different from those in the lab. Different cell types have very different cell wall structures and cell wall strengths. It is important to take that into account. After cell disruption, solid and liquid fractions must be separated once more by using a mechanical separation. That's all for now about mechanical separations. See you in the next lecture for molecular separations.